Hello, my name is Avery Hutchinson, and this is my lab report for our constant velocity lab. In this lab, we recorded the motion of an object moving with constant velocity. The purpose of this lab was to explore the use of Newton's second law to computationally model this motion. I generally found that the constant velocity model was not particularly accurate for my data that I collected. When creating my model, I assumed that only the x component of motion was significant in order to simplify calculations. I also assumed that there were no unbalanced forces acting upon my object that would cause acceleration or change in the constant velocity of the object to simplify my model. Here's the video my experiment is based off of. As you can see, the video was no longer enacting a force to roll the water bottle. In this experiment, I consider the system to be my water bottle and my surroundings to be the earth, ramp, and air. Newton's second law states that net force acting on an object is equal to the change in momentum of the object. Since the object has constant mass, the net force in this situation is equal to the change in the object's velocity over time, which leads to the velocity update formula. In our case, the velocity was assumed not to change over time due to the assumption that there were no net unbalanced forces acting on the object. This leads us finally to the position update formula under a constant velocity, which is our third equation on this sticky note here. To build the model, I needed to gather some data from the original experiment. For one, I gathered the starting point of the object in the experiment, and that point was used as the initial position of the ball. The initial velocity was calculated by taking a small time step right at the beginning of the object's motion and using displacement over time to approximate the initial velocity. The while loop was set to run for the same length of time as the original object's motion, which was 1.42 seconds. From there, the ball's position was updated using the previously discussed position update formula, and the time was updated using a time step of 0.02 seconds. Here are the values that I calculated using the difference in the video's first two data points. So my change in x was 0.0131 meters, my initial time step was 0.02 seconds, and with that I calculated an initial velocity of 0.654 meters per second, and my initial position at time x equals 0 was negative 0.00163 meters based on where I defined my origin. So here's the visual model that I created using VPython. So when I was looking at the actual data that my model was outputting, which is marked in green, I found that the model was somewhat close to the real data, which is modeled in red at the beginning, but the two quickly diverged. So why is that? In the model, no outside forces were acting on the object's center of mass as it moves in the x direction. However, in real life, forces such as drag force and friction act on the whole of the water bottle, which is moving in x and y directions. These outside forces will cause the object to undergo negative acceleration. This can be seen based on how the constant velocity model matches the motion initially, but overall the slope of the real line was much lower, indicating that it had a force acting on it in a direction opposite its motion. Other possible sources of error could have included trouble identifying the center of motion in the video and inconsistent time stepping within the video. So what if? If I switch the axis directions, the magnitude of displacement, which is the magnitude of the slope of the graph, would be the same because the actual displacement over time would still remain the same. It would just be the direction that would change, which would be indicated by a negative value for displacement and velocity. So what does it all mean? My model was based off Newton's second law, which connects observations of acceleration to the net force. This law doesn't give any information about the number of forces that contribute to the net force acting upon an object, so I can't make any statements about those contributing forces or what their relative magnitudes might be. Overall, this was a good introduction to basic physics principles and applying them to computational models, even if my model didn't really accurately reflect my real data. Thank you.